If you look at your hand, you see skin. But if you were to zoom in, past the tissue, past the individual cells, and even past the molecular bonds holding those cells together, you eventually bottom out. You reach the absolute floor of reality. Down in this empty void, we find fundamental particles. These are the final, basic units of the universe, points that cannot be broken down or divided into smaller parts. To define these units, physicists use a framework called the Standard Model. This system identifies every known particle and provides the specific rules for how they influence one another. According to this framework, the immense complexity of the entire known universe, every star, every planet, and every person, is constructed from exactly 17 of these particles. Understanding how these 17 types of matter and energy behave allows us to define the origin of every physical interaction we observe. The first step is to sort these 17 types by the jobs they perform. 12 of them belong to a family called fermions. A fermion is simply a particle that makes up all solid matter. Half these fermions are quarks. Clumping tightly, they form protons and neutrons at the dense center or nucleus of an atom. The other half are leptons. The most famous, the electron, establishes a wide orbit around that central quark cluster. Everything you have ever touched, seen, or interacted with is built from just these two categories, quarks and leptons. But having a collection of building blocks is useless on its own. There must be a system that forces those blocks to stick together or push apart. If you just place a group of fermions next to each other in the void, they will simply drift away. They have no reason to stay connected. That brings us to the second major family of particles in our grid, bosons. A boson is a particle designed solely to carry the forces of nature. Bosons operate by constantly bouncing between the fermions. As they ricochet back and forth, they physically transmit instructions, telling the matter particles whether to attract or repel. This means reality is not a collection of static objects. It is a microscopic crossfire of invisible messengers keeping the universe from falling apart. To see how this actually works, imagine two ice skaters facing each other. If one skater throws a heavy medicine ball to the other, the physical exchange of that object pushes both skaters backward, away from each other. In the subatomic world, a particle called the photon acts as this medicine ball. Photons carry the electromagnetic force, bouncing between electrically charged particles and pushing them apart. But inside the nucleus of an atom, quarks experience a natural urge to separate. To stop this, a different boson, called the gluon, acts as a binder. It rapidly snaps between the quarks, pulling them back together. This high-speed exchange of gluons generates the strong nuclear force. This is the interaction that locks those particles firmly in place. When you knock on a table, you are feeling the result of this process. This high-speed exchange of bosons creates the experience of solid matter in our everyday world. This brings us to a major question. If everything is just microscopic points of data interacting with each other, why do those points have physical weight? The answer lies in the Higgs field. The Higgs field is an invisible energy field that fills every inch of the universe. You can think of this field like a dense, invisible cosmic molasses. Every particle in existence is forced to travel through it. When matter particles, like quarks, move through this field, they drag. That physical resistance is exactly what we measure as mass. Contrast that with photons. Photons slip through this field unhindered. Because they experience zero drag, they have exactly zero mass, which is why light travels at the ultimate speed limit of the universe. Mass is not a property that particles simply possess. It is the consequence of their struggle to move through the universe's foundation. Through decades of observation, the Standard Model has proven to be the most rigorously tested and mathematically accurate theory in history. Yet, for all its precision, the system is incomplete. It cannot account for the existence of gravity, the very force that holds planets in orbit. It also has no explanation for dark matter, the substance that makes up the vast majority of all mass in the universe. We have mapped the structure of every visible object in the sky, yet the most successful documentation of physics ever compiled is still missing its biggest chapters.